Okay, so I start. So I don't see you because I see the mirror of my screen. Can you hear me?
We can hear you very well. We can hear you very well.
Okay. Good, good. So let's start. Oh, well, so it's not charged. Okay, so that is the following question. So I was thinking about how to define a Sandpile group for infinite graphs. And because as you remember, for a finite graph, you can define Sandpile group, and it's a group, nice group, and so on. But then there were articles where they tried to define this Sandpile group for Z2, for the lattice. Why? Because I think the initial motivation was as follows. If you start with a big square, and then you drop grains randomly, then the avalanches obey power law, right?
That's right.
But
I have a little
when you try to
question
prove
though.
it,
I have a little question though. We just see a white screen. I don't see you writing anything.
it's okay.
Yeah, that's fine.
Because
That's fine.
because I charged my pen. Okay, that's for example as a square, n times n, and then when you drop the grains randomly, then you have kind of the following thing that well, I think it's like that more or less. So that's the power law for the avalanches, log of frequency. And so people were trying to prove something about that, but sure, you need to go to infinity. So you need to let n go to infinity, and then maybe the statement must be that you have like infinite plane, and then you drop a grain, and then you make the avalanche. Okay.
Yeah.
But that's not possible in many cases, because if you just put 3 grains everywhere, and then you add 1 grain, and the relaxation never stops.
So worse, it doesn't stop even locally.
Yeah, it never stops anywhere. Oh wait, so somehow my laptop produces a lot of noise, so I just kill all the everything. And then I will share screen again. Diaries of Stiklov.
Oh la la.
Because the Stiklov is the guy who found the Stiklov Institute in St. Petersburg.
Yeah.
And then it became Stiklov Institute in Moscow, the branch of in St. Petersburg. Well, and okay. And like in few years, there will be 100 years after his death. And since I was doing some history mathematics, I decided, well, maybe I should, find his diaries, because he kept diaries all his life. So he has like several thousand of pages of diaries.
Oh wow!
And yeah, so we send the students to archives, archives, and so we have some diaries, but apparently it's not very interesting. So if you just read them, there's a nice part of his diaries about his love affairs. It's quite innocent, so it was like but still it's very interesting to read. And also in the diaries he had like some kind of articles, I don't know, his thoughts on the First World War and on revolution. So and it greatly reminds the current situation also. So when he writes about the First World War, he speaks, okay, so we don't have enough ammunition, our like generals, their treasures, well, they kind of, they're stupid. So it's very much like the current like Russian press, what they write about about the war. Okay, so just okay, so here I return here. So define something for infinite graphs, and the setting is as follows. So like very simple idea that we must have stocks, have things, and if things if the set of things is a CNet, such that for every vertex V in Z2, there exists like S in things, such that the distance between V and S at most C. Then everything works. So what I mean here, so as you remember, like in Misha's talks, we will draw some diagram, and then I explain like everything about this diagram. So first of all, what we need to consider, we consider the following thing. We consider Z bounded gamma. Well, maybe let me write here. Yeah, gamma. So that's if you have a graph gamma and S is a subset of gamma, the set of things. And then this is just this all this set of all functions phi from gamma to that, such that the restriction on S is 0, and there is a constant, well, C, such that the model of phi is at most C. Okay, so that's the bounded functions.
So yeah, this C is not the same C, of course, although we are using the same letter.
Yeah, so I just so for every function there is a certain C.
Yeah, but not only that.
Just
but not only that, there is a C of the CNet that is a different C.
Yes, yes. So let me just write here bounded. Bounded. Okay. Why is that? Well, so later you will see why. It's quite mysterious. So if you take unbounded functions, then it doesn't work. If you take bounded functions, it works. Also, I just want to share that maybe Misha already know that, for example, if you consider Z power n, right? So just all the sequences, that it's not a free abelian group.
So,
but if you take bounds, is a free abelian group.
Could you produce a basis of the last one?
No, so I don't know how to do it, but well, still, so that's a result of 50s, like both of them. Well, I think that there is no explicit basis for the second one, but there is kind of, like existence of a basis.
that is very interesting.
I just learned this.
Is there a reference where one can see these facts, or?
Yeah, I will send. well, not by that reason, but still we have to consider bounded functions. And so you see that's a functions which defined on the whole graph gamma, and which are 0 on the set S of things. Now let's write sequences as Misha like. So 0 goes to the bounded gamma S, goes to the bounded gamma S, goes to C gamma S. So that's the definition. Definition of C gamma S. Okay, so we just write this sequence. I claim that this sequence is exact. So it's exact on the right, because it's the definition of C gamma S. So it's kernel of this map. Okay, so this is this Z B gamma S factor Laplacian Z B gamma S, and Laplacian is the usual one. So right, so if you have a function on a graph and it's bounded, clearly that if you construct well, if you compute the Laplacian at every vertex, again it's a bounded function. So maybe with another estimate, but it's bounded.
One comment.
Both of this.
Sorry. If you compute the Laplacian at sinc, you can have non-zero.
Yeah. So that's true. So that's a good comment. So we have to redefine the Laplacian. So the definition of Laplacian is as follows. So if you, by definition, Laplacian of Z B gamma S to Z B gamma S, by definition, if you have here phi, then Laplacian of phi is the following function, that if you take V not in S, then delta phi of V, well, it's a sum of phi of W, W is a neighbor of V, minus, well, in this case, well, the valency of V times phi of V, okay? And if V belongs to S, then delta phi of V equals 0. Very good comment, thank you. So anyway, still that's a homomorphism, right? So you might think that first we compute the real Laplacian, well, like usual Laplacian, then we take projection. Or you may think that instead of this, we consider functions which defined only on gamma minus S. But well, it's all equivalent. Is it okay, Ernesto?
So this last comment. So yeah, so gamma is just delta is just delta, isn't it? Just the Laplacian. What do you mean by this projection procedure?
But as Misha told, so in our definition, we consider only functions which are 0 at sinks.
That's right.
And if you consider Laplacian at a sinc vertex, maybe it's not 0, but we just define 0 anyway. So because we want to stay in this set of functions.
That's right. That's right. Yeah, but, yeah, I understand. Sinks are sinks, you know. So you could also write.
So we just need to...
You could also write it as Z gamma modulo, in a way, Z of S, right?
Yeah. So yes, we also can write this B, and here we write gamma minus S, something like that.
Yeah.
Yeah, but I prefer to do this. Okay, then let me just erase this thing. Then, okay, so the right-hand side is definition, but still this sequence is exact on the left, and that's non-trivial statement. So here I claim that the kernel of this Laplacian is 0. Why is that? So, for example, again, in most of our applications, gamma is just Z2. So we have this graph, and well, so somewhere we have things. Okay, and for us, so here things will be a CNet in Z2. And let's consider a function phi, and phi is bounded by a constant, let's say a constant m, and Laplacian of phi is 0. Then, how to show that phi is a constant, phi is 0 itself? Well, it's very simple. So suppose that phi is not 0, then there is a point where phi is maximum. Okay, so for example, here my phi is just, well, m minus 1. But then, since phi is harmonic at this vertex, all the other neighbors, it should be also m minus 1. And then after like several steps, I have that it must be m minus 1 at sync, just to have harmonicity. But it's not true, because at sync, my function is 0.
Very well.
Okay. Okay, so you see, so it's quite funny. So it works only, so if I want to have a trivial kernel, I have to consider bounded functions, because surely there are harmonic unbounded functions. They just grow very fast to infinity.
Yeah, also, it's, and you also need this finite distance to the sinks.
Here, no, so because, yeah. So here, I mean, here I need that for any vertex, there is a path to a sink. So here, so far, I don't need this, the distance is the same, but here I need that, yes.
Could be arbitrarily long, okay.
Yeah, so here it's okay if the path is very long. So maybe, so here I don't need that CS is a CNet, but I will need it later. Okay, now let me erase all of that, because I want to draw the sequence. Okay, now the next row, as you may guess, is the same as R bounded gamma S, Laplacian R bounded gamma S, 0, 0. Okay, and now to have that this line is exact, actually I need to show that kernel of delta and co-kernels are trivial. So what to say about kernel? It's just the same as before. Since my function phi is bounded, so it's less than m, and delta phi is 0, then I can find a point where it's very, very close to m, right? So this point phi is equal to m minus epsilon. Let's say that m is the supremum of phi, okay? So here I have a sink, for example. Then, if at this point my function is m minus epsilon, then all neighbors also very close to m. So for every neighbor, I have that here I must have at least m minus 4 epsilon. And then for any other neighbor, I have that here it should be like m minus 4 power 2 epsilon, and so on. But then again, like at C steps, I come to a sink, but I think I have 0, which is contradiction. So basically here I should find such that epsilon less than, I think, 4 power C m must be less, m must be bigger than 4 power C times epsilon. Right, because in every step my function can decrease by just a bit. And C, if I know that in C steps it decreased just a bit, but I arrive to a sink where I have 0, then I arrive to a contradiction. Okay, so it means that the supremum must be.
But
okay, and so
but you don't control m. M is given, right? You don't control it.
Yes, m is given. I
And
can
you
control epsilon.
But how do you control epsilon? Ah, okay.
So if I have a function phi, then m is given, and then I choose the point where the function is very, very, very close to m. Then its neighbors also very, very close to m, but not that close, just a bit far from that, like m minus 4 epsilon. Then at the neighbors of this also it's very close to m, but each time my error grows. But still, if epsilon is very, very small, then in C steps, while I go to sync, there's error grow not too much, but I think I must have 0.
Yeah.
And so if, for example, at this vertex I have like m minus 2 power n 4 power c epsilon, then still, so here I cannot have harmonicity because one of the neighbors is 0. But again, it must be close to m. Okay?
That's right, that's right. Just by choosing epsilon less than m times 4 to the minus c.
Mm-hmm. Yeah.
Very
Misha,
nice.
is it okay? Misha.
Yes.
Yeah, it's
Okay.
very nice, very nice.
Good. So that was a kernel. Now it's even even more funny for co-kernel. So as I said, so here now I want to show that the Laplacian is invertible, basically. Right? That's what I need. So I want to show that for every, let's say, psi in R B gamma S, there exists phi such that delta phi equals psi. Well, I do it later. Okay, but that's also true.
So are you going to use some
Because
Green's function here or not?
No, but actually what happens, yes, so apparently there are good Green's functions here and they decay very fast, and that's why basically I can define like phi as just psi convolution, the Green function. Well, that's possible to do, but I think that the Green functions indeed they decay very fast, but I don't know how to prove it. So my proof will be direct, like which you can give to a high school student. Basically, I will construct solution. So yeah, but apparently that's because the Green function exists and it decays very fast.
Yeah, it's what.
Okay, so now
it's a little bit from the previous argument. You know, if you, it feels naively that just the previous argument you did, where you have a control on this epsilon, if you kind of dualize this argument, gives you this fast decay for the Green's function. But you have a different argument.
But more, right? Okay, there's just a question. Isn't it enough to prove it just for delta function, right? Which is one.
Yeah, but I don't know how to do it for delta function.
Okay.
Well, maybe, but again, so if you do it for delta functions, so here you have bounded functions. They are not necessarily with finite support. So then you have to prove that if you sum up the like infinite number of these like solutions. Well, I don't know how to do it in another way, but well, I will just give you some explicit construction, but a bit later.
Okay.
Okay, so here let's assume that we proved it. But now the rest is quite automatic. Again, now you see, so what happens if you factorize bounded functions which are integer valued, real valued by the integer values? So then here you have S1 power gamma S. Right, so if you just take functions which are not bounded, then you cannot do that. So you cannot factorize just Z power gamma by R power gamma. Well, R power gamma by Z power gamma. It makes no sense. Well, so you can, but it's not equal to S1 power gamma. No, okay, so That makes sense. Yeah, that's okay. But if you have here, let's say, bounded, it's not true. Well. Anyway, that's how I arrived to that definition, basically. Well, that's the only definition that works. Definitions they don't work. Okay, so here you also have this S1 power gamma S. You have here delta. Here you have 0. Like similarly here, delta is surjective, right? Because if it's surjective for real numbers, then it's also surjective for S1 valued functions, right? Because you just take a solution for reals and then you take it mod 1.
That's right.
And then here you write harmonic functions with values in S1 on gamma S. These are harmonic functions. Such that the harmonic on gamma minus S, let's say phi here. Phi is harmonic on gamma minus S. So 0 on gamma minus S. Phi is 0 on S. But maybe delta phi is not 0 on S. Maybe.
You see, it's very confusing how you use this Laplacian. Here you really refer to the ordinary Laplacian, and just above the same sign denotes this restricted Laplacian.
Yeah, you're right. So you suggest to have another notation, I think.
Yeah. Just I don't know. You choose, but I would decorate somehow this new Laplacian. So
Like delta S.
Okay.
Or maybe like delta S. Oh yeah, no. If I find this sign symbol, then yes.
Yeah.
Yeah, fine. Good
Well, I
like it.
yeah, it's so funny that yesterday I wrote this same picture for a different, not totally unrelated reason, you know. So it is very amusing. Anyway, yeah, very nice.
So anyway, so now we have just theorem that C gamma S is just the harmonic functions as F1 gamma S. It's Snake's lemma. And basically what happens, so here you take a state phi, then you do delta minus 1 of phi mod 1. Right, so if you take state here, so you first consider it as a integer valued state, just take any representative, then you consider it's a real state, then you take Laplacian minus 1, then you take it mod 1, and your function is harmonic. Okay? And that was also contained in Har and others, like article of 60 years. And it was like Solomiak, like 98. Then it was like Verbitsky, Schmidt, like 2008. And then it was like Shkolnikov and Lenk, 2000 something, like 2018. Right, so people rediscover the things many times. I think it's well, quite natural. So Misha, so this formula was introduced by Har, and the idea was the following. So you know the story, right?
No.
So they introduced this exactly this thing because they wanted to have invariance for elements of Sandpile group. Because if you so here like motivation of Har was the following. So if you have a function alpha which is harmonic, on your graph. And then you have a state phi, gamma to z. And then if you compute just alpha times phi, it does not change if you apply, well, it's mod 1, I think. If you apply topplings, so alpha phi null mod 1 equals alpha phi. So it does not change when you make perform topplings.
Okay.
Exactly, because mod 1 means that, well, like at every point, for example, here, your function is for alpha equals B1, B2, B3, B4. So when you perform a toppling, if you have such identity, then this product, it does not change. So here I mean just summation, alpha times phi, it's equal to sum over all v, alpha of v times phi of v. So maybe it's scalar product. It's better to do it like that. Okay.
Yes.
Well, so that's a set of invariants. So that's how they compute the order of the group. So they just form the matrix delta minus 1, and then they computed the generators of this matrix. And generators of this matrix, that's exactly this relations on well, classes of equivalence. So in a sense, that's a dual group. So here you can find case, you can
Pontryagin dual or something.
Yeah. So exactly. So here you say that home from like C gamma S to I think S1, just the same as H S1 gamma S for final graphs.
Yeah, and then you
Right.
show that this Sandpile group is actually self-dual in a canonical way.
Yeah.
That's what you do.
Yeah, well, so that can be done for final graphs because this sum, well, is finite, but you cannot do that for infinite graph, right? So because for infinite graph, the sum may be infinite, and maybe you can do it like for subgroups, maybe for subgroups of something. I think yes. So if we take harmonic functions which decay very fast at infinity, then still we can have this scalar product, but not for every harmonic function, right?
Yeah. Yeah, you will.
Okay. So that's the statement. It was algebraic part, and now let's do Sandpile story. Now it's Sandpile story. So which I found before. Oh well. Also, by the way, all this is joint work with my student, with Vladislav Khramov. It's a funny story. So I have a student, and maybe I've never talked to him in person. We always communicated through Telegram. So maybe it's chatbot. I don't know. Yeah. So once we have a call, so we but he has no video, so I only heard his voice, and
you never know. You never know.
Yeah. So Sandpile story is 4. So my graph is just Z2, and so here I have sinks, and it's a CNet. And now let's say that I have a state phi, I have a state psi that are sets from gamma minus S to Z, bigger equal to 0. And then I want to define phi plus psi relaxation. So actually what I will do, I will show that if I add two Sandpile states, and if things form CNet, then the relaxation will terminate. So what I mean by terminate, I mean locally. that like if I have phi set gamma minus s to z bigger or equal than 0, I said it's relaxable if there exists f bigger than 0, f also from gamma minus s to z bigger or equal than 0, such that phi plus delta f is at most 3 everywhere on gamma minus s. Okay, and then the relaxation function is pointwise minimal of such f. Okay, so it means that I want to make certain finite number of tokens at all vertices, at every vertex. So maybe like the total number of tokens will be infinite, but locally it's finite. For every vertex, I have only finite number of tokens. Okay, so how to do it? I just show that for every, let's say, constant m, there exists such function f from gamma minus s to z bigger or equal than 0, such that the Laplacian of f is -1 everywhere. Well, and then it immediately shows that any bound state is relaxable, right? Because then, oh, so here no any m, and then if phi less or equal than m, then phi plus m delta f is no more than 3. Okay, so it's enough to find such function f with negative Laplacian everywhere. Okay.
Very good.
Well, how to do it? I just constructed. So we have that S is a CNet, and then I just define that if the distance between V and S equals K, then f of V by definition will be I think 4 power c plus 4 power c minus 1 and so on plus 4 power c minus k. Okay, and then let's check what happens. So if here I have a sinc vertex, here I have V, so it has 4 neighbors, and at least one of the neighbors is closer to V, and one of the neighbors is far, okay. Then when I compute delta f of phi, it will be what is that? It is sum of w f of w minus 4 f of v. Right, and so now let's see that I want to show that it's at most 1, minus 1. So I need to estimate from above. And I think here I can estimate it as 4 power c plus 4 power c minus k minus 1 plus 3 4 power c plus 4 power c minus k minus plus 1. Here it's plus 1, here it's minus 1. Because for one neighbor, so here maybe the distance is k plus 1. So for at least one of the neighbors, I have, yeah. See, I think it's for, so okay, what I want to say. Yeah, I want to say that for at least for one vertex, the distance is k minus 1. because there is a vertex which is closer to S, and that is this one. And all other three, they may be they at most this one, right? And also I have to subtract 4 power c plus 4 power c minus k. Well, and now the final step, I have to compute it accurately. Like most of these terms, they disappear. And what is left? Actually, it left 3 times 4 power c minus k plus 4 power c minus k minus 1 minus 4 power c minus k. And that is, so you see, so this, okay, that is just, oh, wait. No, it's okay. So here I have 3 power c minus k minus 1 minus 4 c minus k. Okay, good. And that is, well, less, just 4 power c minus k minus 1 times 3 minus 4, which is less than minus 1. That's it.
That's right.
So basically, it's just very simple. So, and here you need that for all the vertices, you have the same estimate, right? Because your sum started with c power c, 4 power c. So if for different vertices you have different estimates c, then you don't know what to do, because they may be like this very long chains, and here each term it's like 4 times less. So if I want that my function is integer valued, I must have have finite number of terms, and so the maximal term must be like very precise. So if I don't care about that my function is integer, so here
Do we hear Nikita?
I think he froze. I was wondering if it was me. I'm going to stop recording.
So now I want to solve such equation, and what I do, well, I do it like as a sequence of functions. Just define phi null equals minus m times f from above, and this delta phi null is bigger or equal than m everywhere.
Yeah. Nikita?
Okay, no. Yeah. Can you hear me?
Now you're back. Now you're back.
Yeah, like that. So phi null is bigger than 0. Also, I may assume that phi is bigger than 0, right? So since my delta is linear, it's enough to solve only for positive psi, and then, well, for negative psi, for mixed psi, I just take a sum of the corresponding solutions. So I take I take a function phi null, just mf, and it has a Laplacian less than m minus m. But at some point, well, I wish to have that Laplacian is psi. So what to do? So if I have at some point I have delta phi null less than psi of v, what I can do, I can just diminish phi null of v, right? So I take phi null of v, and then I take at phi null of v minus some constant, I don't know, like k. Then delta of this function phi 1 at v will be bigger than delta of phi 1, phi of v, right? So if I just diminish my function phi at a point, it will increase its Laplacian at this point, right? Because Laplacian, it's sum of neighbors minus 4 phi of v, right?
Yeah.
So what to do? Well, I will just decrease the function at every point. And so maybe I even can write what I want, right? So I want to have that my Laplacian is psi, and now my Laplacian is less than psi. So at every point, like phi 1 of v will be phi null of v, and I want to decrease it minus 4, no, minus delta phi minus psi of v minus delta phi null of v divided by 4. So that's so I just decrease my function at all points such that like it will be like more equal to what I want. And then again, so in this procedure, I have that phi 1 is less or equal than phi null, and still I have that delta phi 1 will be less or equal than psi everywhere, right? Because if I decrease my function only at one point, I can make it equality, but maybe also I decrease my function at neighbors. So I not only decrease this thing, but also I decrease these things. And so if I don't decrease neighbors of v, then I have equality. So I have this equality here. But if I also decrease the neighbors, then I still have inequality here. And well, then I just proceed the similar way. So I just define next function as well, similarly. This minus psi minus delta phi n divided by 4. And so I have this thing. I have that phi n plus 1 is less than phi n. I have that delta phi n is less or equal than psi, but also that here the most important thing. I have that phi n is bigger or equal than minus mf. So what I mean here, you see that so my function cannot be too negative, because if at some, so for example, again, if I just decrease it by 1 point, so when I decrease my function at 1 point to make the Laplacian right, this value cannot be less than minus mf, because if this would be less than mf, then the Laplacian of my function at this point would be very negative. So you see, so if I have the several points and I decrease here function too much, then still I have this inequality, and I just take the first point where this function phi n is less, v is less than minus mf. Then at this point, I have delta phi n of v will be bigger than m times minus 1. Which is not true, because always I have that delta phi n is less than psi.
Yeah.
And so I have an estimate from below. So I have a sequence of functions decreasing and with estimate from below. Then they have pointwise limit, just infimum of phi n pointwise. And clearly delta phi infinity is psi.
And here you need just to divide by 4. That's very interesting. You see what I mean? Because of integers, you couldn't do that.
Yes.
But it's funny that you need to be able only to divide by 4. I would believe that you need much more of a real structure.
Well,
Yeah,
but
imagine
a graph. Imagine a graph that has valencies of all prime numbers. An infinite graph with valencies all prime numbers. It's still a rational structure. It's totally rational, but
yeah, but for such graphs, such function f does not exist. So here, what I need, that function f, which I construct here, this function f exists if all the degree of the valencies of vertices less than some constant c1, and S is a C2 net. So I cannot do that if the valencies are arbitrarily large. Because actually here, instead of 4, I must put the maximum of valencies. So actually here I should have like f of v equals C1 power something plus C1 power something and so on.
that's right. I see what you mean. So yeah, it is very interesting that it's not about the reals, it's about the rationals, and not really about the rationals. It's about a certain localization of the integers.
Exactly.
Yeah, but then I have to take the limits, right?
Sure.
Still lives in certain localization, doesn't it? Yeah.
Well, so maybe you can do it at 2 adic numbers, right?
Yeah.
It will be two adic Sandpiles.
Something like that. Well, yeah, it's funny, but it's maybe has something to it. Maybe.
Yeah, it's a very nice comment. Okay, but so you see, so that's exactly what we did. So like now we first of all we show that any two functions like at two Sandpile states the relaxation is defined, and also I proved that the theorem above that here the sequence is exact. And then you see, then you can construct everything as usual for Sandpile states. So for example, now you can define the following. So define definition. Phi is recurrent if phi plus beta relaxed equals phi, where beta is just a function equals 0 equals like k, well, let's say 1 on neighbors of S and 0 otherwise. Right, so as usual, so if you have a sink, then you put beta is just 1 here. If you have another sink, you also put just 1 to the neighbors. And you do it for all things. So like formally, beta is defined as Laplacian of -1 on gamma on -s. Okay, so just take a function which is -1 everywhere and compute its Laplacian. And it will be this one. Okay, so the state is recurrent if you have that, then the identity is equal. Maybe here you take like something like 4 power c beta relaxed. Like if you have a state alpha, then minus alpha is just minus alpha plus like a large number of b relaxed. So you have just all the same. So the same as you define the recurrent states for finite Sandpiles.
It is still It is still
It's a group.
free.
No, it's not free. So here, let me also present a theorem.
It's a torsion group.
Theorem 1.
The torsion. Mm-hmm.
Yeah, sometimes torsion, sometimes not. So
Why?
one can choose.
Wait a sec.
Choose C such that C of this Z2C has no torsion.
Oh, well, that is very interesting.
So basically the idea is as following. So let me draw one more diagram that you will like. I think both of you will like it. So what is a function of order, let's say P, right? So here you have harmonic functions. So here you have S1 power gamma S. Well, even gamma I can write here. So a torsion is when you find a map. Torsion if here in S1 valued function, if you have a function which has denominators, which has all rational values with denominators n. Well, let's say that phi n equals identity if for every vertex v, phi times n, well, is 0 mod 1. So phi of v is equal to k over n. Okay, so it means that torsion subgroups, like, so instead of phi, consider phi tilde equals phi times n mod n. And then if phi was harmonic, mod 1, then phi tilde is a function phi from gamma minus s to zn, harmonic on, well, gamma minus s. So it's a usual function which is harmonic, but now its values in a finite group. So instead of looking for Sandpile states like which are finite order, I can just look for the groups for the functions from my graph to Zn which are harmonic. And what we want to do, we want to construct a graph such that there is no harmonic functions like that. Let me give you an idea how to do it. So it's okay if I speak more.
Please, it's very interesting.
Yes.
Yes. So I will give you, let's say, this example, how to do it. I consider such a graph. It will be just things everywhere outside of it. And let me have here another tower. So I want to construct a function which is harmonic, right? So let's suppose here I have, let's say, like a. Then if this function is harmonic, then here I must have 4a. And then here I should have what? I should have like 15a, right? Because 4 times 4a equals a plus 15a. Right? That all, it's kind of mod n. But what I want to tell you that it determines all the elements here. So if I put any element here, then it determines all the elements in this tower. This tower just this line. This vertices have valency 1. Okay. Is it clear?
Yes.
Yeah.
Then at some moment I must have 0, right? Because if I have the sequence which each term defines the next one, then at some moment I must have 0, because you can think that I start with 0. So here is 0. The first term is 0, then something non-zero, and then all that.
Yeah.
Then let me choose the height of this tower just to have 0 here. I can do it.
Very well.
Right?
Very well, yeah.
And then let's suppose that here I have this like minimum number d. So like I have this period d. So if I start with 0, then after d steps I have 0 here. And let's suppose here I have d minus 1. And here I have the same situation. Here also I could start with some number b's, and here I have 4b and so on. But then I must have 0 here, not here, and here should be not 0. So the only possibility is that b equals to 0. And all the elements here are zeros. Right? Because here, no zeros.
Yeah.
And if I encounter a 0 inside of this tower, then all the elements in this tower are zeros.
Yeah.
Okay, so here it's 0. But then it means that if here I have some element, let's say c, then also here I should have minus c. And then again, so here in this part, I also have this sequence. And if here I put d minus 1, and here I have the same tower power d, and here it must be also 0, because here I have d, then this c also must be minus c must be 0. Because also I start with 0 and have after like these steps I must have 0, but I must have 0 here, not here. So c is 0, so a is also 0.
Yeah.
Well, and then so the proof is as following. So you just need to do it like simultaneously for all n. So you start with this thing, and you put some towers here, then some towers here, some towers there, and then you kill more and more like finite subgroups.
Okay.
Yeah.
Okay.
Still, let me also explain you one more sequence, which also I enjoy a lot. It's quite counterintuitive, but you will see now what's going on. Where it's the sequence is here. Let me just complete it just a bit. So what is a finite? What are the elements of finite order? As I explained to you just now, it's just the same as here. We have a map from Zn power gamma s, delta s, Zn power gamma s. And so here you have this harmonic functions in Zn gamma s. Right? So if this is not trivial, so that's a torsion and torsion in Sandpile. Okay, and so in here my maps are quite simple. So here I sent 1 to 1 over n. Right? Just to get an element in the circle, I just divide by n. Now, I think also you both will like what happens next. Now I want to dualize these groups. So what actually all the functions from what are the functions from my graph to Zn? Actually, that's that equal the home from Zn finite gamma s to Zn from Zn finite gamma s to Zn. Right, so because if I have a, so also here, so there's just dual Laplacian. Because if I have a, well, Zn gamma s, it's functions with finite support. For example, delta functions and all of what they generate. Okay, well, because if I have such a function, so I prescribed, so if I have such a homomorphism, it means that I prescribe a value for every delta function. So if I have phi from here, then phi for delta v is some number, let's say k, and then I just define that, well, just the same as a function, you know, psi, which of v equals k. So I can prescribe the values for every delta functions. It's the same as prescribe values to all vertices. And now the funny part. So let's consider one more sequence, this one. So here I have sequence Zn finite gamma s. I have this Laplacian to here, Zn finite gamma s. And okay, so now I speak about Laplacian for functions with finite support on Zn. And the question is following. So here I have 0 only if here kernel is equal to 0.
Mm-hmm.
Oh, well, wait. No,
Co-kernel.
No. Co-kernel, yes. So if here is co-kernel is 0, then when I apply home, then I will have 0 here. Right? Because when I apply home, it reverts the errors. And so what does it mean? It means that so no torsion if delta is surjective here.
Yes.
No torsion. So what does it mean? If delta is surjective, it means that for any delta function, I can solve the delta phi equals some delta function. If it has a solution for every vertex, then I don't have a torsion in my Sandpile group. And so what does it mean actually? Let's see. So here in this example, let me try to do it. So here it means that if I have such a thing, it means that if I put somewhere 1, then I can devise a function which has Laplacian exactly 1 at that point. So I can find a function which has such a Laplacian. And if you look at the construction above, so it means that you just have to do all the same, but then at some point here you have this twist. So you change your function. You have not Laplacian 0, which I wanted here, but you add 1, and then you don't have these contradictions with zeros. So you don't have this abstraction to extend your function. At least for like your function will have a finite support. It will be with support here. Or if you want to have the value 1 here, then your function will have support here. So you see, instead of thinking that we just build these towers to kill the torsion, you can think that we build such towers such that for any like harmonic function like that, for any delta function, we could find explicit solution on a small part of the picture, like with finite support.
That's funny.
So,
very nice, beautiful.
It's very funny. So I don't know how to generalize this. So that works like for primes, and is prime. Right, because maybe if you apply home for not field, maybe it's not exact. I don't know.
Yeah, you have some extensions.
Yeah. Yes, and well, and also I think what else? Also, I wanted to say something. Ah, no, it's okay. So yes. So no harmonic functions in the n. It's the same as you see. It's funny. No harmonic functions with values in the n. It's the same is the Laplacian is surjective for functions with finite support.
Very nice.
Well, and the last theorem, maybe I will not give you the proof, but I can. It's fast. Another theorem is that if you consider S is a set of, let's say, I, N, J, N, where N is fixed, and here I, J, and Z. So you just remove from the plane, the points like periodically. Then
like a sublattice.
Yeah, just remove the sublattice. Has all torsions. Well, and here what you do, so instead of z square minus s, you just factorize your plane to have an infinite cylinder, like that, with things. And then you show that since you know that for any big part of it here, you have non-trivial solutions for harmonic functions in well, d2 minus s to the n, delta phi equals 0. So for any part here, you have non-trivial solutions because you can well, for example, because you have zero solution, it's always a solution, and the dimension of, let's say, the dimension of the space is bigger than the number of conditions, right? So you have condition for every vertex inside, but here on the boundary of this finite part, you have more free variables. So it means that if you have zero solution, you have another solutions, because solutions is a hyperplane through zero. Of non-zero dimensions. And then since you have solutions for every big finite part, then at well, you can show that you can find solution which is periodic, that here it's the same as here. And then if you find such solutions that at some moments they have just repeating patterns, then you just repeat it an infinite number of times.
Yeah, this period.
And that's how you obtain solution on a cylinder, and then you obtain solution on the whole plane. Well, that's all what I wanted to tell you. Maybe the last remark, that why also I became interested in that, okay, so if we know that this function has all torsions, then how to distinguish such groups, right? So, well, we have a group which is infinite, which has all torsions. And why I like such as, because here we have an action on Z2. And so we can find entropy. And I think that entropy will be different. So, well, there are articles about entropy for this infinite Sandpiles on Z2. So actually, it's not Sandpile group. They just define all recurrent configurations on Z2. They have measure on this set, and then they've computed the entropy for the action by translations. And I think also here, also one can compute this entropy more or less explicitly, and it will be different for different n. And that's why you can distinguish these infinite groups which have all torsions.
Yeah.
But that they have different action of a group.
That's fascinating. This last part about the entropy. I would love to learn more about this thing in the future.
Yeah, I like to understand what's going on.
That's a work in project. So I just wrote that to Evgeny Verbitsky. That's exactly this article with of Verbitsky and Schmidt. When they where it was, maybe I also erased that. Yeah, well, so there's an article about entropy for harmonic functions on Z2 with S1 valued. So entropy for harmonic functions with values on S1 on Z2 is computed, was computed. That's Verbitsky, Schmidt, like 2000 something. And that's yeah, I can tell you the answer. So here you see, so if you have a harmonic function, it means that you so kind of this system is generated by polynomial 4 minus 6 minus 6 minus 1 minus y minus y minus 1. And then the entropy is just equal to the integral over S1 of the logarithm of f of xy. And that's equal to something like, 2 minus, well, integral from 2 minus 4 cosine, well, it's just this expression. So you can integrate it explicitly, and there's some number. And that's, well-known story that if you have a dynamical system generated by a polynomial, then you can compute entropy very fast. And you can write such polynomials also for this periodic lattice. So, for example, if you have, well, you can do it. So maybe it's not quite simple to find the integral for different polynomials, but still it's all well known. So if your dynamical system is let's say is defined by a polynomial, that you consider functions such that the convolution with this polynomial is 0. That's exactly the definition of like harmonic function, right? So if you can, well, no, it's not convolution, right? So it's kind of your like symbolic convolution. Well, but you understand what I mean, right? So you say that if I have a function alpha and I present it as like phi, well, alpha of ij times x power I, y times j, and then harmonic function means that if I multiply it by f, I have 0, right? Or something like that. Yeah. And that's mod 1. That's harmonic function on and so, like, if we don't care about the meaning of entropy, that can be computed. So I don't understand why entropy is given by such formula. That's called Mahler measure. Measure. Well, I don't understand why it's true, but.
So sorry, I need to go. So.
Yeah, sure. Well, I finished.
Fantastic.
Yeah.